AJ, what are you guys doing in organic these days?
So, I'm confused because we're about to have an exam. We just got done with ethers and oxides and aromatic rings. Now we're moving on ketones and aldehydes.
Okay.
And it's just like the final chapters, all the reactions. It's just super reaction heavy right now.
Yeah.
So, yeah, it's just sheer memorization.
Yeah.
So,
Yeah.
it seems like once you get to that point, though, like that organic 1 and 2 is definitely, if you struggle with prior chapters, you're going to struggle with as you keep going along, like everything builds on each other.
Yeah.
Like I feel like now, if you have a good understanding, you can kind of like eyeball some reactions and see how they're going to go.
Yeah, for me, I always just had to memorize the stuff. I had no innate talent for organic reactions at all.
Yeah. I think I like it just because it's a little break from math heavy science.
Yeah,
classes.
yeah. I think organic chemistry is always one of the indicators for med school because there's so much stuff you got to memorize and all that kind of. I think med school is kind of the.
I'm definitely not a morning person.
You're not.
I'm not a morning person. It was rough.
Isn't it true that if you like Gen Chem, you won't like Chem, and vice versa?
Yeah, I don't know. They're very different. One of the last chapters we're going to do is just kind of like a brief bit of organic chemistry, but that's mostly just the nomenclature so that you understand what some of the terms mean. Like I talked about amines and carboxylic acids and things like that. The thing I never understand about this is, and this is why I don't think I could ever write a chemistry textbook, is I don't understand what order you really should go in. Because every time I think I have the right order figured out, I get in the middle of it and then I'm talking about something and I'm like, oh, we should have talked about that before. You know, I mean, it's so intertwined that there's not a real clear, at least to me, a real clear 1, 2, 3, 4 type thing. And you talk to different people and they have different opinions on what order things should go. And, you know, some of the stuff everyone agrees on, like the stuff you do in the very beginning of Gen Chem 1, that's pretty much the same for everyone. But like, after this chapter, we're gonna go back and talk about some more thermodynamics. Well, we've talked about thermodynamics chapters ago, and now we're going back to it. And some people would argue, why are you doing that? And and that's valid. We still have to do some electrochemistry. Well, some people like to do that a little earlier. So the organic is just different. And really, when people think of chemistry, they think of organic chemistry, of doing synthesis. And some people like that, some people don't. I'm an analytical chemist by training. So organic kind of drives me crazy because analytical is real precise and you use a lot of instrumentation and it's measurements and all that. The organic guys, 2 grams, 2.2 grams, that's close enough type thing. analytical people, that makes our skin crawl. And so, and I'm exaggerating a little bit on all that, but you know, they have a different view of things.
That class started off totally like organic one was, you ended the semester with just heavy reactions. Organic two starts off and it's NMR, mass spec, all these different machines and
Yeah.
reading the results. So that was different, but now it's right back to tons of equations.
And see, even that part, the organic guys do it different than we do. Because I teach instrumental analysis. I'm teaching that this semester, and we do NMR and we do infrared and we do all that stuff. But ours is more of a quantitative thing. Like the organic guys like to use NMR to track their reactions.
Yeah.
You know, and all they're looking to see is, well, is this peak going away and this one forming? And, you know, they'll do it some for some structure elucidation to see if they made the right stuff. But it's still, it's a qualitative type thing. Analytical people, if they do NMR, more often than not, it's like a quantitative NMR. So I don't know. It's just whatever you like. And then if you take physical chemistry, that's a lot of that stuff from a math perspective. And so it's heavy on math. So.
A lot of people say, like, I guess the assumption of organic chemistry is it's so hard. It's really not that bad if you just put the time, if you're willing to put the time.
It's a lot of time. It's more time than Gen Chem is. And so, but that's where it gets that, the actual material, I don't think is that difficult. It's a lot of it. And a lot of it is you gotta memorize certain things. And then some people like that, some people don't. So, all right, we're gonna. Okay, we're gonna go ahead and get started. Can the people on Zoom hear me and see the slide?
Yes.
Thank you. Okay, so what we're going to do today is we're going to finish up chapter 17. And then that means on Thursday of this week, we'll have the third exam, and that'll cover chapters 15, 16, and 17. So once again, finish up chapter 17 today. And then on Thursday, we'll have the exam over chapters 15, 16, and 17. So when we left off last class, we were starting to talk about buffers, and we talked about the Henderson-Hasselbalch equation to be able to calculate pH for buffers and some things like that. So we're going to continue on and finish up the buffers, and then we'll talk about titrations and solubility product constants and some things like that today. So when we talk about buffers, there's a term known as buffer capacity. And so you can have things that are technically buffers, but some can buffer more acid or base than others. And that's really what buffer capacity is saying. And that is always linked back to the concentration of your buffers. So that buffer capacity is telling you how much acid or base the buffer system can neutralize before you see an appreciable change in pH. If we look at the Henderson-Hasselbalch equation, we see that the pH for a conjugate acid-base pair, where each of them are 1 molar or each of them are 0.1 molar, would be the same. So that pH value would be the same regardless of whether the conjugate acid base were each 1 molar or 0.1 molar. what the difference is in those two buffer systems is that one that had the conjugate acid base pair where each was 1 molar would be able to neutralize more acid or base. So in other words, neutralize it and keep the pH constant. So in that case, you would say the 1 molar solution, base solution, has a greater buffer capacity than the other one, the 0.1 molar. When we think of buffers, there's a range that buffers are effective. And that is based on the pKa of whatever that buffer system is. And so the rule of thumb is that if you're going to make a buffer and you want to use it at a particular pH, it needs to be plus or minus 1 pH unit around the pKa. So if the pKa is 4, then the buffer needs to be between 3 and 5. And then you'll have good buffering capacity. And what this comes from is if you think back to that Henderson-Hasselbalch equation, is you want, remember we said we want the acid concentration and the conjugate base concentration to be roughly the same. And then in that case, you get to where optimal pH is pH equals pKa, if those are roughly equal. If you get more than 10 times, if that concentration ratio, acid form to conjugate base, is out of whack by 10 times or more, then that's when the buffer system kind of falls apart, and it's a pretty weak buffer. That translates into this plus or minus 1 pH unit from pKa. So the thing to remember on this is, to be an effective buffer, there's a couple things you need. One is you want those concentrations of the conjugate acid base pair to be roughly the same, and the pH you're trying to buffer at should be plus or minus 1 of the pKa. If you get outside that, you really don't have a very effective buffer. And if you have too big of a difference in those concentrations, the buffer doesn't work very well either. And I guess the final thing I would add is what we talked about on the previous slide, is that the more concentrated that conjugate acid base pair is, the stronger, the more buffer capacity it has, the stronger the buffer is. So when you have a buffer system and you add either a strong acid or strong base to the buffer, really what you have is you have a neutralization reaction. So that strong acid or base will get consumed by the buffer system. You can calculate the stoichiometry problem to find HA. So in other words, the acid and the conjugate base after all the acid base reacts. You can then also use the Henderson-Hasselbalch equation to find pH. And we'll go through an example of this. The other thing I want to say about the Henderson-Hasselbalch is you can use that to calculate this pH of the buffer, but you don't have to use it. You can just treat it as a normal equilibrium problem. So whichever is easier for you. So let's take a look at an example here where we have a buffer that has 0.3 moles of acetic acid and 0.3 moles of sodium acetate. And then it's added to enough water to make 1 liter. So the nice thing about that is we're in molarity. And then we want to calculate the pH after 0.02 moles of sodium hydroxide is added. So we've got a buffer system, in this case acetic acid. The concentrations are the same, so that's a good thing. And then we have sodium hydroxide that we're adding, and sodium hydroxide is a strong base. So we had said that for these types of problems, what we want to do is we want to go ahead and see the impact of neutralizing all that sodium hydroxide, and then that'll give us our new equilibrium concentrations. So if we kind of set up this equilibrium table like we've been doing for different types of problems, we have our acetic acid, our hydroxide, and then our acetate ion concentrations across the top. We have our initial before the reaction, so that's 0.3 moles of acetic acid. We're adding 0.02 moles of hydroxide, and 0.3 moles is what we start with of the acetate. So before anything happens, that's the number of moles of each that we have. Well, we do that, and now we see we're going to react this hydroxide with the acetic acid. So it's going to use it all up. So 0.020 moles of the acetic acid will react with the hydroxide. That hydroxide will get used up, so we'll have 0 afterwards, so that's a minus 0.020. The LR in parentheses just stands for limiting reagent. We talked about limiting reagents in the past. And so this is just telling us that all of this stuff is going to get reacted. If that much of the acetic acid gets reacted, then we're going to produce that amount of moles of acetate ion. So we go ahead and do our subtractions or additions from before and then change. And that tells us we now have 0.280 moles of the acetic acid. As we said, we've used up all of our hydroxide, so we don't have any of that left. And then we have 0.320 moles of the acetate ion. Okay, so we could use Henderson-Hasselbalch equation if we wanted to. The concentrations, as I said, are the same. It's a buffer system. It's 1 liter, so moles and molarity are going to be the same. So we could go ahead, we could look up our pKa for acetic acid. We could plug in the concentrations for the acetate and the acetic acid. That would be the A minus would be the acetate ion. The HA would be the acetic acid. So if we go ahead and plug those values in, then we would get a value of 4.80. And what you want to note is our pKa is 4.74. Our pH is now 4.8, so it's pretty close. And that's reflected by these concentrations of the acetate and the acetic acid being pretty similar. So let's take a look at this from a base perspective. So let's talk now about adding a base to a buffer system and see what happens. And one of the things we're going to do is we're going to look at it if we would add that base to just water versus adding it to a buffer system. And I think that'll really highlight how buffers are used to control big changes in pH. So if we have 5 mils of 4 molar sodium hydroxide, and first we're going to add it to 1 liter of water. So if we want to find out how many moles of hydroxide, and then ultimately the hydroxide concentration, we need to take our 5 mils, and so 5 mils is 5 times 10 to the minus 3 liters. We convert that mils into liters and then multiply it times the molarity. So now we've canceled out our liters, because remember, molarity is moles per liter. So we'd cancel out our liters in the denominator, and we'd wind up with 2 times 10 to the minus 3 moles of hydroxide. Well, we started with 1 liter of water, and then we added 5 mils of the base. So now our total volume is 1.005 liters. Okay, so that's the 1,000 mils of water plus 5 mils of the base is 1.005 liters. So what we need to do is then divide our moles by this 1.005 it doesn't change it a lot, but it does change it a little bit. And so then that tells us our molarity is 0.00199 molar hydroxide. We can go ahead and then find the pOH of that if we want. You get 2.70. And remember 14, pH plus pOH has to equal 14. So if we subtract that 2.7 from 14, then we see the pH is 11.3 of this solution. We say that pure water has a pH of 7, right? So we see that adding just 5 mils, 2 times 10 to the minus 3 moles of hydroxide, just adding that small amount of hydroxide into water shifted the pH from 7 to 11.3. That's a pretty big change, right? So this is why people are interested in buffers, because buffers can prevent from having these big kind of pH shifts. So let's take a look at this. A similar thing, if we add hydroxide, in this case, we're going to add it to a buffer system. So we add that same amount of hydroxide to a buffer system that's 0.3 moles of acetic acid and 0.3 moles of acetate. Well, we know from back here, it's 2 times 10 to the minus 3 moles of hydroxide is what that works out to, because we're adding the same amount to the same volume of solution. So we know that then that means 0.002 moles of acetic acid will react with that base. That's similar to the previous problem we went through. And we know that the acetate will increase by that amount. It'll go from 0.300 to 0.3002. So now we can plug these numbers into the Henderson-Hasselbalch equation. So this minus the log of 1.8 times 10 to the minus 5, that 1.8 times 10 to the minus 5 is the Ka of acetic acid. 0.302 is our acetate ion moles. 0.298 is the acetic acid. And we go ahead and we solve this and we get 4.75. So originally the buffer concentrate pH was 4.74. So we see by adding that same amount of base to an acetate buffer system, we had a change of 0.01 versus, what was it again? For the water, it was, what is that? 3.7 units. So this is the idea of having buffers, is to be able to have a system that can handle some disruptions in terms of acids or bases coming into it. And, you know, I think most biological systems are some type of buffered system, and this is one of the reasons for it. It helps control the pH. Usually reactions like to go at particular pHs. And so if you think of it like a biological system, you want to control those pHs so that whatever that biological reaction is needed can take place. So that's the main idea about buffers. Any questions about buffers before we move on to titrations? Okay, so I know last semester in lab there were some titrations. I think the classes have been doing some titrations this semester. So hopefully a lot of what I say won't be new, that you'll be familiar with it and be comfortable with it. But let's just go ahead and talk about titrations for a bit. So as you know, titration is you either have an acid or base in your burette that you're titrating with, and then it's the opposite. If it's a base in your burette, then it's an acid in your solution, or vice versa for the acid-base titrations. I will point out that there are a host of other types of titrations. They're not always acid-base titrations, but that's what we're going to focus on here. Have you guys done any non-acid base titrations in the lab this semester?
Did a redox.
Did a redox one, okay. So that's the basic idea with titrations. When you're doing these acid-base titrations, you either can monitor them with a pH meter or you can use a chemical indicator. But in each case, what you're looking for is the equivalence point. And the equivalence point is when the amount of acid equals that of the base. So which do you think is easier for you? Monitor it with a pH meter or an indicator? You like the pH meter better? How about on Zoom? Did you like the pH meter better or the indicator better?
The pH meter.
pH meter, yeah. So just to tell you this is that other than in like Gen Chem class, anymore you don't use the chemical indicators very often. You might use them just for a visual because it's kind of a pretty thing to watch, but it's almost always a potentiometric titration like that. The other thing I'll tell you, which you won't like hearing, is most people don't do manual titrations. There's something called an auto titrator, which automatically titrates reading the potential. So the mechanics of it probably be a little different if you go on in chemistry and do it, but the principles are all exactly the same. So that's why it's important to kind of understand what's going on. So if we talk about a strong acid, titrating a strong acid with a strong base, you should get this type of titration curve that we see on the right. And it's kind of like this where it goes slow, slow, slow pH change. And then as you get near the equivalence point, it's a pretty sharp rise, and then it flattens out again in the middle, in the top. And in the middle here of this vertical climb portion, I'll call it, right in the middle of that is your equivalence point. And for strong acids and bases, those titrations, that should be at pH 7. We'll see in a bit for weak ones, it's not at 7. There's reasons for that. And so hopefully this titration curve looks familiar to everyone. And then if you were trying to figure out what that volume was, you would take your equivalence point, you'd extrapolate down to the x-axis, which in this case is milliliters of sodium hydroxide. And then through that mils of sodium hydroxide, you could calculate out how many moles of acid you had. If you titrate a strong base with a strong acid, it looks very similar. It's just kind of backwards because since it's a strong base, you're going to be starting up at a high pH. In this case, it's a pH 13. It goes over where the pH doesn't change much. Then as you get near that equivalence point, you have a pretty steep vertical drop, and then it levels off again once you get past the equivalence point. So once again, whether you're going strong acid with strong base or vice versa, you'll get these curves that are pretty easy to look at because you have a pretty good break. Usually you get a pretty good equivalence point at 7, and they look like this, either flipped one way or the other, depending if it's an acid base or base acid type titration. Now, you can also titrate weak acids and bases, and that's where it gets a little bit not quite as well defined as the strong acid, strong base. And the strong acid, strong base, as we were saying, your equivalence point is at 7. You get usually a pretty sharp curve. It's usually pretty easy to pick out the equivalence point. The weak ones sometimes aren't always as good. And part of that is because if it's a weak acid, you're going to have some type of buffering going on, right? Because remember, that was kind of our definition of buffers. It's a weak acid-base system. So if we're going to do a titration of a weak acid with a strong base, we can use the Ka to find the initial pH. And then we can find the pH in this buffer region using the stoichiometry followed by the Henderson-Hasselbalch equation. For these types of things, the pH is usually greater than 7. And we use the conjugate base of the weak acid to determine the pH. Moles of the base added equals moles of acid. And the conjugate weak base reacts with water to form some hydroxide. And that's why you'll be a little bit above 7 usually. And it varies depending upon what you're titrating, how far above it goes. So the curve will be similar to what we saw with the strong acid-base titrations. But what I want to point out is a couple things. One is if we look at the start, we see more of a slope on the start of it. And that's common in these types of titrations. And also we see in this case, it looks like it's a little bit above 8 is the equivalence point. And once again, that's based on what that conjugate base is and that generation of some hydroxide there. And then the top part looks pretty similar where it kind of flattens out once it gets past all that. So we can calculate the pH when some of the weak acid is neutralized. And so we calculate the moles of the weak acid. We calculate the moles of the base added. And this will tell us the moles of the anion that's formed. And then we'll do that subtraction to see how much acid is left. And then we use the Henderson-Hasselbalch equation. This is exactly the same calculation that we just did a few minutes ago, okay? That's what we did when we added some strong base to it. So it's the same calculation. And I hope that's the thing you're kind of getting on all these. There may be little twists on it, but it's basically the same calculation over and over. So if you get comfortable setting it up, and I really do think that little table that we've been setting up is the key, because then it kind of lays it out for you. If you get in the habit of doing that, I think usually you can work through the problems. So this is what I was saying before about the weak acid curves are often a little harder to kind of see than the strong acid curves. And on this plot here, we've got a series of acids. At the very bottom is a strong acid, and we see that's where we have our typical kind of not much change in pH till it gets near the equivalence point, then a big uptick, and then it goes over. But as the acid dissociation constant changes, and so 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, 10 to the minus 8th, of course, would be the weakest acid. And so now what we see is a couple things. One is we see that initial pH is going up, okay? So as the acid gets weaker, the initial pH that we start with goes up. The other thing we see is this area, this kind of like equivalence point area. It's a little hard. Like I look at the one that's 10 to the minus 8, the top one. And that gets a little trickier to figure out exactly where that equivalence point is. At least to me it does. And especially when I compare it to the strong acid one, where I have that nice long straight portion and it's easy to pick out the middle. So that's the other thing you notice. The other, a final thing I would say is you see that this equivalence point goes up as the acids become weaker. So this one that has a Ka of 10 to the minus 8, that equivalence point looks like it's, I don't know, 10 and a half, 11, somewhere around that. And so that change is smaller for the weaker the acid. And in general, picking things out when that change is smaller is a little more difficult. And the equivalence point creeps up above 7 as you go to weaker and weaker acids. So we talked a little bit about, do the potentiometric titration where you use a pH meter to measure the potential and plot that versus the chemical indicators. Chemical indicators, as we've said before, they have a color change over a certain pH range. And if your equivalence point happens to be in that range, then the chemical indicators work fairly well. But you have to have the right indicator. The other thing that's a little tricky about the chemical indicators, which I think everyone saw in lab or has seen in lab, is that sometimes a real small volume change can have a bigger impact on that color change of it. And so it's easy to miss your endpoint. I don't think you do this in Gen Chem, but you can do what's called a back titration if you miss it, and then bring it back, and you can just go back and forth if you do that. But in Gen Chem, we don't do that, I don't think. So let's just talk a little bit about what we mean about that indicator choice. So last semester did acid-base titration and used phenolphthalein. The phenolphthalein change is somewhere around 8 to 10 in that range. And what you see is that you need a titration curve where equivalence points are going to be in that 8 to 10 range. So here's a couple examples of one equivalence point. Looks like it's about 7.5. Another one looks like it's at maybe 5.5 or 5 maybe. And using a phenolphthalein indicator, well, you certainly could do that. You could use it because it would eventually change colors when you got up to in the 8 range. But that's not really telling us anything about what you're trying to do in this particular titration. So phenolphthalein would not be a good choice for things that have equivalence points at these other ranges. Now we see on the right-hand side, there's an indicator called methyl red, and that changes color in this, looks like it's about 4.2 to 6 range. And this equivalence point looks like it's at about 5 or so. So that's a case where that one would work okay there because you would get that color change around the area that you'll want. We talked earlier about polyprotic acids. And one of the ones, so you think polyprotic acid, so that could be sulfuric acid, H2SO4, it could be phosphoric acid, H3PO4. So the sulfuric acid has 2 protons that it can donate. The phosphoric acid has 3 protons. So each of those have more than 1 proton that can be donated. And so that's what we're talking about when we talk about polyprotic acid. And those polyprotic acids, you can titrate and see each of those equivalence points. And more importantly, you can get the pKa's from those. And so let's take a look at this titration curve that's on the example here. So we have an acid, looks like it's starting at about pH 1, and it's titrated for, and this first equivalence point looks like it's roughly maybe about pH of 4. So you have your first equivalence point. Then you go keep titrating, you get your second equivalence point for this one. That looks like that's at about pH 11. What you see is that if you go and see for this first equivalence point, we're estimating it to be 50 milliliters. If you go to half of that volume, in other words, 25 mils, that is the pKa for the first proton. Okay, so in this case, I don't know what that is, maybe about 1.8 it is, 1.9, something like that. As you go and then continue titrating to go to that second equivalence point, if we extrapolate down there and say that's 100 mils of sodium hydroxide, the difference between 50 and 100, so going from the first equivalence point to the second, that's 50. So then you would go halfway over, which would be 25 mils plus 50 mils, takes you to 75 mils. And we extrapolate down and up to the curve there, and that's our second pK value, our pKa2. And that looks like it's a little over 6. So one of the things you can get from these titration curves, and especially with like the polyprotic acids, is you not only get the equivalence point, but based on how much material you had to titrate with, you can get pK values. And sometimes people use that to kind of identify to make sure it's the right acid if they're not certain or not. Then if it was phosphoric acid, for instance, you could continue on and find the third pK value if you wanted to. So key takeaway here is the pKa value is going to be, you find your equivalence and what that volume is, go to the halfway point, and then that pH tells you what the pK is. When you go to the second one, it's not, you don't start from the beginning when you do that calculation, you start from that equivalence point. And like I said, in this case, it was 50 mils. You go to the second equivalence point is 100, 50 to 100, that's 50 total. You go to half of that is 25. The 25 plus the 50 brings you to about 75 mils, and that's your pKa2. Okay, any questions on that? What I'd like to do now is talk about a couple of homework problems. So the first one is 1721. So in 1721, we're asked to calculate the pH of a buffer that is 0.12 lactic acid and 0.11 molar sodium lactate. So in this case, and the other thing we need to know is the acid dissociation constant for lactic acid, which is 1.4 times 10 to the minus 4. So we can use the Henderson-Hasselbalch equation, pH, because it's a buffer system, pH equals pKa plus the log of, in this case, the lactate ion divided by the lactic acid concentration. If we go ahead, so remember, pKa means minus the log of the Ka, right? That's what the P function stands for. So if we go ahead and do minus the log of 1.4 times 10 to the minus 4, we get 3.85. So we plug that in for our pKa. So now we have 3.85 plus the log of that ratio of 0.11 to 0.12, and we get a value of 3.81. Then the second part of the question is calculate the pH of a buffer formed by mixing 85 mils of 0.13 molar lactic acid and 95 mils of 0.15 sodium lactate. So in this case, it's going to be a similar thing, but we have to calculate out what the molarities are based on the information we've got, because we're combining some solutions. So for the lactic acid, we need to have the 85 mils into liters, so that's 0.085 liters, and then multiply that times the molarity of the solution, and that puts our numerator into moles. The denominator needs to be in liters, and so if we have 85 mils of the lactic acid solution and 95 mils of the sodium lactate solution. We want to add those two volumes together to get our total volume. Once again, working in mils, it's 0.085 plus 0.095. And then we do that math to get a molarity value of 0.061 molar lactic acid. We'll need to do a similar calculation to get our lactate concentration. So there it's the 95 mils of times the 0.15 molar. The mils has to be in liters, so it's 0.095 times 0.15. Now we have moles of the lactate ion, and then divided by that same total gives us 0.079 molar lactate ion. So now we've got molar concentrations of our acid and the conjugate base. So we can go ahead and plug those into our equation. So we have over here on the right-hand side, we have log of 0.079 divided by 0.061. The pKa we already calculated in the first part of the problem. Now it's 3.85, so we'll just put 3.85 in there. And we go ahead and we finish our math and we get a value of 3.96. So here's an example of where we use Henderson-Hasselbalch to calculate out pH of a buffer solution in two different instances. One thing I want to just point out is, okay. All right, let's go on to 1741. What I was just going to mention is there's another way you can do that calculation, okay, without using the Henderson-Hasselbalch. I think it's a little easier using that equation, but there is another way, just doing the normal kind of making the table and doing the normal equilibrium expression and all that stuff. And that is in the homework. It's worked both ways in the homework if you want to take a look at that. Like I said, I do think this is a little easier way to do it. Okay, so let's look at 1741. So how many milliliters of 0.0850 molar sodium hydroxide are required to titrate each of the following solutions to the equivalence point? And the first one is 40 mils of 0.09 molar nitric acid. So what we would want to do is we would want to calculate how many moles of acid are we dealing with. Okay, so nitric acid is a strong acid. So this is going to tell us how many moles of protons we have to titrate. So we need to have it into liters. So we change our 40 mils into liters. So 0.04 liters times the molarity, which is 0.09 moles per liter, to give us 3.6 times 10 minus 3 moles of HNO3. We know from our reaction 1 mole of acid reacts with 1 mole of base, so we have this 1 mole sodium hydroxide, 1 mole nitric acid relationship. And then we can then use our molarity of the sodium hydroxide, 0.0850 moles per 1,000 mils, because we want the answer in milliliters. And then that will tell us how many mils of sodium hydroxide we're going to need. And that answer is 42.4. So the things we used here is we remembered we need to work in moles per liter. So we had to do some conversions of mils into liters. We had to think of the reaction stoichiometry. So sodium hydroxide, strong base, HNO3, strong acid. It's a monoprotic acid. So it's a 1-to-1 molar ratio on the stoichiometry. And then if we get comfortable with all that stuff, then it's just a matter of dimensional analysis to make sure our units are being canceled out correctly to get to the final answer. Okay, in part B, we have 35 mils of 0.0850 molar acetic acid. So in this one, we have our liters, or we've changed our milliliters of acetic acid into liters, so it's 0.035. We calculate that, multiply that times the molarity. We use our 1-to-1 molar relationship. And then finally, we use our concentration of hydroxide to come up with 35.0 mils of sodium hydroxide. So once again, a similar type thing. Question C, exactly the same approach. So I'm not going to go through with that. The only difference there was we were given grams of HCl. So we know we need to be in moles. So in that case, you needed to convert the grams of HCl into moles of HCl. So you would have had to have calculated out the molecular weight of it and used that. Okay. Let's shift gears a little bit and go to solubility and solubility equilibria. So the thing I want to point out on this is even though now we're talking about solubility rather than neutralization and things like that, it's still, these are still equilibrium expressions. And so kind of that fundamental way of writing equilibrium expressions and all that, that still carries through for what we're doing in this part, okay? If we have ionic compounds, remember we said those are strong electrolytes and they dissociate completely. So they have complete dissociation to the extent that they dissolve, okay? So if it's above the solubility, then they're not going to dissolve anymore. But what they dissolve to will be complete. That's for the ionic compounds. When we write equilibrium expressions with the solubility stuff, think of it as the solid is the reactant, and then the dissociated ions are the products. And remember, one of the things we said when we wrote those expressions in the past, if something's a solid, we said it was 1, and it didn't show up in the equation, right? So that's why I'm saying is we're really not introducing anything new here. We're kind of doing what we said before. We're just giving it another name. So KSP is the solubility constant. And so as you probably have noticed, we have a lot of different Ks. We've got KSP, we got Ka, we got a lot of names for these equilibrium constants. But what they all have in common is they're all equilibrium constants. And so the idea of how we work with them in that is really going to be pretty similar. So once again, don't get confused by all the different types of equilibrium constants. They have different names, like this one, KSP, solubility constant. They have different names, they have different values, but the concept is the same. Okay, so let's look at a solubility product. So in this case, we have barium sulfate, which is a solid, and we know that because of the little S in parentheses, going to form barium +2 and sulfate -2 ions in solution. So we write that equilibrium expression. KSP equals barium ion concentration times sulfate ion concentration. This would be divided by the barium sulfate concentration normally. Well, but it's a solid, and we said a couple weeks ago, if it's a solid, it's a 1, and it doesn't show up in our expression. That's why it doesn't show up there. Let's look at the next one where we have barium phosphate. What's interesting about this is now we have some coefficients in our dissociation reaction. We have 3 barium +2 +2 phosphate -3. So when we write that KSP relationship, we have the barium ion concentration times the phosphate ion concentration, but we have to go back to the stoichiometry on our equation and see that, gosh, we have a 3 in front of the Pa +2, we have a 2 in front of the PO4 -3. Because of those coefficients, we have to raise those concentrations to those powers. So for this KSP, it's barium plus 2 concentration cubed and the phosphate ion concentration squared. Once again, that's the same type of stuff we did with our other equilibrium expressions, okay? We looked at the stoichiometry on our balanced reaction. And like we said a few minutes ago, in this type of expression, we're saying the solid's the reactant, the ions are the product. So it's products over reactants. We look at that balanced equation, and if there's any coefficients out in front, then we have to raise those concentrations to that power. Okay? So technically KSP, the solubility product, is not the same as solubility. When you talk about solubility, you're talking about stuff like grams per liter or moles per liter. You're talking about how much stuff, okay? The solubility product constant tells you how much would go into solution, okay? They're pretty similar, but they are technically different. So don't get confused by that. Solubility would be, I'm weighing stuff out, I'm putting it in, I'm trying to see how many grams I can get in per liter. The solubility constant gives you a feel for how much will dissolve. And the key thing here is the solubility constant, if it's little, tells you only a little bit dissolves, okay? So if I gave you a bunch of solubility constant values and said, which of these will dissolve the most? Well, it would be the one with the highest solubility constant. The lowest one would mean not very much dissolves. If I wanted to know how much that was, then that's where I would do a solubility experiment and get a grams per liter or moles per liter type of number. So there's a subtle difference between the two. To be honest, the KSP is what people usually look at, because that gives you a feel for how much stuff's going to go into solution. It doesn't tell you the number, but usually you just want to know, is this going to go in a little bit or a lot? So that's where the KSPs come in handy. Let's go ahead and do a calculation of KSP. So here we're told for calcium fluoride, the KSP is 3.9 times 10 minus 11. What's the molar solubility? So once again, we write our reaction out. So in this case, we have calcium fluoride going to calcium plus 2, and then 2 moles of fluoride ions. We write our KSP expression. So it's the Ca plus 2 concentration times the fluoride ion concentration. Because we have this 2 in the balanced equation in front of the fluoride ion, we have to go and raise that concentration to the second power. And then that's equal to the KSP value, which we were given at the beginning of the problem. So we treat this as an equilibrium type of problem. So we set up our table here: calcium fluoride, calcium ion, fluoride ion. We don't have an initial concentration. Why? Because it's a solid, right? Initially, we have 0 of the ions. We put it into solution, we're going to have some change. That change is X. For the calcium, it's 2X for the fluoride ion, because that for the stoichiometry in the reaction. And then the equilibrium concentrations will just be X and 2X. So what we can do then is plug those values into our KSP expression. So here we have X, which is the calcium ion, 2X, which is the fluoride ion. That has to be squared. So we do all this math and we get that that's equal to 4x cubed. So the only tricky thing here really is, can you use your calculator to find the cube root of something? So make sure that you can do that type of calculation with your calculator, that you know what keys to press, because that's not one you do every day. At least I know I don't. So that's the only, so setting it up hopefully looks pretty straightforward to you. It reminds you of things like we've done in the past. But finding cube root, I don't know if we've done that yet this semester. Okay. We said early on when we started this chapter that one of the things is the common ion effect and how that impacts solubility. So let's talk about that a little bit. So when we're talking about common ion, and in this example, it's calcium fluoride, CaF2, and we're seeing how that solubility changes as we add, in this case, sodium fluoride. So in this example, the common ion is the fluoride ion. We have fluoride that comes from the dissolution of the solid calcium fluoride. So remember that dissolving, according to its KSP, is going to have calcium +2 and fluoride minus. But now we're adding some fluoride minus because sodium fluoride is going to dissociate as well. And we're going to have more fluoride in there, fluoride ion in there. If we just go back here to a second and look at our KSP, we know this KSP value, in this case 3.9 times 10 to the minus 11, we know that that doesn't change, right? It's a constant. But what does change are these concentrations here. If we're adding something in here into this fluoride minus concentration, that's getting bigger, then the calcium +2's got to get smaller in order to maintain that ratio to give us our 3.9 times 10 to the minus 11. And sure enough, that's what you see happening. We start up here and we see that in pure water, we're at a value, I don't know, between 10 to the minus 4 and 10 to the minus 3. As you're adding sodium fluoride, so in other words, more of that fluoride ion, we see the solubility going down, okay? Down, 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 down. So when we get down to 0.2 added of the sodium fluoride, we're all the way down to about, I guess that's about 10 to the minus 9 is the solubility. So in other words, by adding that fluoride ion, we're pushing the equilibrium back the other way to maintain that KSP value. The same thing would happen if someone would have added calcium ions, okay? There's nothing magical about it being the fluoride. It could be either the fluoride or the calcium. Either way, it's going to push that back. And the end result is you decrease the solubility of that solid that you're trying to dissolve. Let's go ahead and do a calculation of solubility with the common ion. And so we're going to calculate the molar solubility of calcium fluoride in 0.010 molar calcium nitrate. So in this case, the common ion is going to be calcium. We write out our equation, same as before. We write out our expression, same as before. Okay. And then hopefully right now you're saying we're going to make our table. So we make our table again, calcium fluoride, because it's that solid, doesn't participate in this. We're just putting it there so our bookkeeping looks good. Then we have calcium +2 and fluoride that we start with. Okay, this calcium +2 comes from what we said in the beginning here, is that we have 0.01 molar calcium nitrate. So that's the 0.01. Then there's some change. So, and the change is coming from the KSP expression from the calcium fluoride. So some amount's going to increase, some amount is going to increase of the calcium, and some amount's going to increase for the fluoride ion. We know that's 2x because of the stoichiometry of the equation. And so now we're going to add these up. And we get the new equilibrium concentration of the calcium plus 2 is 0.01 plus x, and the fluoride is 2x. So to solve things, we go ahead and we plug in our values that we got from the table, 0.010 plus x, 2x squared. We're going to make an assumption here that that concentration doesn't change a lot, and so it's going to allow us to neglect the plus x on the 0.010, and so it makes our math a lot easier. So now it's 0.010 times 2, that quantity, 2x, that quantity squared, and then we can solve for x and get 3.1 times 10 to the minus 5th. We go back and check. If x is 3.1 times 10 to the minus 5, and we compare that to our 0.010, it was a pretty good assumption that that really doesn't impact it. So it was a good assumption to make that x is a lot smaller than that 0.010. Okay, another thing about pH, it affects solubility. And I'll tell you, a general rule of thumb is, and this is where the pKa's come into play, is a general rule of thumb is, if you know the pKa of something, and then you know the pH of what the solution is, you look to see if it's going to deprotonate something or protonate something. And if it does one of those, ionize things in general, dissolve in water better, okay? And so that's where, and so whether it's acid or base or whatever, that relationship between protonating or deprotonating things, how pH affects that, and like I said, that goes back to the pKa. Because the other thing I'll point out is the pKa is where the molecule wants to be. So whatever that value is, if something has a pKa of 5, it wants to be at 5. It wants that solution to be at 5. If you get away from that value, it's going to either donate protons or pick up protons to try and get it back to 5. That's the whole idea behind the pKa and the buffer and all that kind of stuff. It'll do that till it's exhausted. And so that's why knowing the pH that the solution is in tells you a little bit about if it's going to be soluble or not. Because if you can get stuff ionized, like if it's the carboxyl group, you deprotonate it, it's going to be more soluble. If it's an amine and you keep it protonated, it's going to be more soluble. That's just rules of thumb. Okay. We talked a little bit about Lewis acids. And as I said before, we're not going to stress the Lewis acids a lot. But remember, one of the things we said that Lewis acids can form complex ions. And that was, we talked about that when we talked about the metal ions. And so because of that, that allows some of these metal ions to have increased solubility of their salts. And here's just a table of some metal complexes. We see first we have some silver, then aluminum, cadmium, chromium, cobalt, on down the line. Over on the right-hand side is the chemical equation for that, okay? And then we have the formation equilibrium values on the middle here under the KF. And you can see some of those are pretty good, pretty big numbers. We look at this aluminum hydroxide, and that's 10 to the 33. That's a big number. So that's telling me that, boy, it really likes going to the right. And so those formation constants give us a feel for how likely it is for these complexes to form. And you see with these metals, at least all these on here, pretty favorable going to the right. Because remember, equilibrium expression would be products over reactants. If it's a big number, that means the products are favored. Here's just some more metals. Once again, you see some pretty big numbers there. The iron with the cyanide, there's a couple of those. Those are pretty big numbers. So you can sometimes, by doing some of these complexations, you can impact solubility of things. So in this case, we're talking about silver chloride. So silver chloride, AgCl, is insoluble. But you can make it soluble, at least get some solubilization, by adding ammonia to it. Okay, and then you form this silver ammonia complex, and that has solubility into it. So silver chloride that's a real common titration to do chloride amount. So if you want to know how much chloride is in something, you can add like silver nitrate to it. The silver precipitates out the chloride, and you can determine how much chloride is in there that way. So silver chloride's insoluble. It's telling us it has a KSP of 1.6 times 10 to the minus 10. So that's telling you not very much of it goes into solution, just a tiny amount. Essentially, it's insoluble. You add that ammonia to it, because that silver ion, the silver can form complexes with ammonia, you're actually able to solubilize some of it. So there are oxides and hydroxides that are amphoteric. And what amphoteric means, it can be solubilized in either acids or bases. And aluminum, chromium, zinc, tin, those are some examples. I think I'll leave that at that. Okay. One of the things that you're interested in to use the KSP value for is to understand if the concentrations of the mixture you have, if things are going to precipitate out. We've been thinking about KSP in terms of dissolving stuff, right? That's kind of how we've been thinking of it so far. But really it goes the other way too. Depending upon what that relationship is of the ions, say you had the ions together, it would tell you, if you add more of one of them, are you going to start getting a precipitant or not? And that's a lot of times what people want to use KSPs for. And so remember before we talked about something called Q, the reaction quotient, where we would go ahead using the conditions that we had and calculate out what that equilibrium value was, and then compare it to the equilibrium constant. Well, you do a similar thing with the KSP to see if something's going to precipitate out or not. So we have our equilibrium expression set up like we normally do. We'd plug our numbers in and we'd calculate that Q value. If Q equals the KSP, then everything's at equilibrium, and those concentrations, you just say it's a saturated solution, nothing's going to happen. If we do that Q calculation and Q is less than KSP, okay, then that means you could put more solid in there. You could get more solid to dissolve. You could So no precipitate forms. And then finally, if Q is greater than KSP, then you're going to have precipitation there. So similar approach when we use Q before on understanding equilibrium, if things were at equilibrium or not. Because remember, in this case, we're still talking about equilibrium. We're just talking about if we're going to start getting stuff precipitating. The other thing that can happen is you can have something that is soluble in a particular solution, and you can add another ion into it. And I'm not talking about a common ion or anything like that. It could be a totally different ion. And some of these different ions will then cause other things to precipitate out. And we don't do it here, but this is often a Gen Chem lab experiment. They give you an unknown and you got to figure out what's in it. And it's based on following, and I'm not going to go through this scheme. You can look at it if you want. But it involves going through this scheme of where by adding different reagents, you start precipitating things out. And like I said, you can read through this and see, but by precipitating things out, you can sort of figure out what the ions are. And that's taking advantage of this mixed salts, mixed ions can result in selectively precipitating out some things and not other things. And so you can kind of do this flow chart on the right here where it says you have unknown metal cations, you add acid, you're going to precipitate out some of them, some of the metals, silver, lead, mercury, then go down, add some other reagents, keep going down, down, down to where you can figure out what group it's in. Okay, I'm going to spend just a few minutes going over a problem or two, and then we'll wrap up. Okay, so let's look at 1751. So 1751 is write the KSP relationship for these compounds. Takeaway here, once again, is we treat this as the solid is the reactant. The products are the ions that it dissolves into. And so what we would have is the first two, silver ion times I minus, second one, strontium times sulfate. The third one, though, is because there's 2 moles of hydroxide, 1 mole of iron, we have hydroxide minus squared. The fourth one is Hg2Br. Don't worry about that. Hg2 is a really weirdo thing. Don't even think about that. Okay, 1755. You have 1 liter solution saturated with calcium oxalate, and it contains 0.0061 grams of calcium oxalate. And then calculate the KSP for this salt. Okay, so first thing we do is we write our dissociation expression. So we have our calcium oxalate going to calcium plus 2 and oxalate minus 2. We were given grams. And so we know when we do this kind of stuff, these KSP expressions, these equilibrium expressions, we got to be in moles. So we'll go ahead and calculate what our molecular weight of calcium oxalate is, and that's 128.1. So we can change that 0.0061 grams into moles. And it's 1 liter, so we get 4.76 times 10 to the minus 5 molar. From our reaction, our dissociation reaction, we know it's 1 mole and 1 mole. So when we go to our KSP expression, we know that the calcium and the oxalate ion concentrations will be the same. That's that 4.76 times 10 to the minus 5 value. Multiply those by each other, and we get KSP of 2.27 times 10 to the minus 9. Okay. And let's look at 1769 here, at least the first part. We want to know, will calcium hydroxide precipitate from solution if the pH of a 0.05 molar solution is adjusted to 8? Okay, so if the pH is 8, we can calculate out the pH, the POH is 6. Do you remember pH plus POH has to equal 14? So now we have a hydroxide POH of 6. That's equal to 1 times 10 to the minus 6 molar. So now we know the hydroxide ion concentration. We can write our KSP expression. Cobalt concentration times the hydroxide squared because of the 2 coefficient in front of that. And so we want to calculate out a Q value. So we have 0.05 molar calcium coming from our calcium chloride. We have our hydroxide concentration calculated from our pH through POH. And then we get a Q value of 5 times 10 to the minus 14. We're told you have to look up the KSP value. That's in Appendix D3 of the book. But you look up that KSP value, you get 6.5 times 10 to the minus 6. 10 to the minus 6 is a lot bigger than 10 to the minus 4th, so the KSP value is bigger. So that tells me there's no precipitation going to occur. All right. Any questions about any of this stuff? So please take a look at the homework, work through some problems. And just a reminder again, Thursday won't be any class. Thursday will be the exam number 3. As usual, it'll be posted in Canvas and you'll have the time during the class period to take the exam. And that's it for this today. Thank you.